let's look at what a KSP value is good for. You can compare the KSP values of different substances to compare solubility, okay? But that only works, it's only a direct comparison for compounds that dissociate into the same number of ions, okay? You can't compare KSPs of something that dissociates into 2 ions versus something that dissociates into 3 ions because of the exponents that are in there, okay? But if the number of ions is the same, then you can compare. So with these ones, are these all ones that we can compare together? What do you think? Yep, these all dissociate into 3 ions. Okay. Now, look at those KSP values. Remember, KSP is a calculation from the concentration of the ions that are dissolved. Okay? So, if I want to find the one that is the most soluble, I need to find the KSP value that is what? Yeah, I need to find the highest number here. What's more important to look at, though, the number in front or the power of 10? The power of 10 you should look at first. Which of these is the largest power of 10 listed here? Yeah. Okay. So this one is the most soluble of these. Be careful. What if we were comparing 2.45, 10 to the minus 5 versus, I don't know, 4. Oops. 10 to the minus 5. Which one of those is more soluble? Yeah, 4 is. So I see a lot of mistakes like that. Picking out the largest number of something that has a negative exponent is something sometimes you have to think a little bit more about. Okay. Sometimes I second guess myself when I think of these, and all I do is write it out in standard. 0.0000245, 0.0000400. That's clear which one is larger. Right? So think about that. That's sort of all I'd say there. There's an interesting thing that you can do, though, with a solubility equilibrium. You can drastically change the outcome of the equilibrium by adding things. Okay? You can make it so something that was totally dissolved will completely precipitate, or vice versa. Something that was totally insoluble can be made to dissolve by manipulating the equilibrium in a Le Chatelier's principle type sense. Okay? So here is our calcium hydroxide solubility equilibrium. Right? There's its KSP value. To that solution, we're going to add some calcium nitrate. Okay? Either as a solution or just as a solid or whatever, it doesn't matter. We're going to pour some calcium nitrate in there. And we have to think back a little bit to solubility rules, because sodium, potassium, ammonium, nitrate, and acetate make compounds totally soluble. They're the solubility equivalent of strong acids or strong bases. Okay? They're completely dissociated, so there is no solubility equilibrium for them. It would be infinite. Okay? So when we add calcium nitrate, you have to make sure that you write that as calcium 2+ ions and 2 nitrate ions. Here, we don't need a parentheses there. Like that. Okay. And then what we're going to look for is to see if any of these ions that we're adding are common with any of the ions that are present in the solubility equilibrium that we're talking about. Okay? So here, nitrate doesn't matter. Spectator ion. Not involved in this equilibrium up here. But essentially what we're doing is increasing the concentration of those calcium ions, which are a product of that equilibrium right there. Okay? So this is the common ion. For the two compounds. All right, calcium hydroxide, calcium nitrate. The calcium ion is the common ion between these. Okay? So, from Le Chatelier's principle, which talks about adding or removing something from an equilibrium, if we add calcium ions to that equilibrium, which direction is this reaction going to go in response to that? Is it going to produce more calcium ions? Or is it going to try to get rid of some of those calcium ions that we've added? Yeah, it's going to try to get rid of them. Okay? If we add this one, add a product, the reaction shifts to the left in response. The equilibrium will shift in a direction that tries to counteract whatever change we've made. So if we're adding a product, the reverse reaction will speed up to try to eliminate that excess that we've added. Okay? So the reaction shifts left in response. Okay? So adding a common ion to a solubility equilibrium will increase or decrease that compound's solubility. If I'm shifting that equilibrium to the left, have I made that compound more soluble or less soluble? Less, because I'm forming more of this solid right here. Okay? So that will decrease a compound's solubility. So we could have a saturated solution of that calcium hydroxide where it's just been dissolved. And if I add anything else that has calcium ions in it, it'll go to the left and we'll see calcium hydroxide precipitate. Okay? So we can induce an ion to precipitate by increasing the concentration of that ion in solution.
So if you added calcium, the solid, would it go the other way? Have less?
Yeah. Well, if you added the solid, you would, let's see here, how would that work? You're still bound to this KSP. So if the solution is saturated, you can increase those concentrations to a certain extent, but if multiplying them together exceeds that KSP, then it won't dissolve. So we'll talk about that here in a second. We'll talk about decision making when doing precipitation reactions. So let's do a calculation here that demonstrates the change in solubility for a substance with a common ion. So let's calculate S for calcium hydroxide. Let's start out with this. Calcium hydroxide, OH parentheses 2, solid, at equilibrium. Okay. Then why don't you write the ions that are produced in solution and make an ice table really quickly. Then substitute the KSP value. And get that in terms of your S's and eventually solve for S. gonna solve for S. What'd you get for S?
1.05 times 10 to the negative 2.
Yep. And what unit does that have? Molar. Okay. That is the solubility of calcium hydroxide in pure water. Okay. From its KSP value, we can use the S's and 2S's and stuff to get its solubility in pure water. Now go down here, write that same equilibrium. Calcium 2 plus O2 OH minus. The difference here is that we want that calcium hydroxide to be in a 0.10 molar calcium nitrate solution. And that's going to affect our ice table. It's going to affect the values in our ice table. So, anybody have any ideas where this 0.10 molar is going to show up? Yeah, that is initial for calcium concentrations. Okay, hydroxide is still going to be 0. We're still going to do plus S and plus 2S, but now we got 0.10 plus S and 2S. Doesn't seem like much, but this is going to change our calculation a huge amount, because 4.68 10 to the minus 6, 0.10 plus S, 2S parentheses squared. Okay, and we could multiply through and distribute, but we're going to end up with a quadratic equation because there will be an S squared and an S and a number. Is there a shortcut we could do that works most of the time and allows us to not need to solve a quadratic equation? Yeah, we can say if S is small, if S is small, what can I eliminate here? Yes. All right, that is 0. So 2 squared is 4 times 0.1 is 0.4 times S squared. So you can see at this point there's already a big difference here. Up here we said KSP equaled 4S cubed. Down here that same KSP is equal to 0.4 S squared, which is going to end up being a pretty huge difference. S is going to be then the square root of KSP divided by 0.4 square root 1/2. Anybody get a number? What'd you get?
3.42 times 10 to the negative 2.
Yeah, that's what I got. Let's do, got a concentration there. Let's do 2 sig figs. 3.4, 10 to the minus what? 3? Okay. How does that value compare with the one we had up above in pure water? It's smaller. I was going to say N. S is smaller than the one up there in pure water, which means that that calcium hydroxide is more soluble, less soluble? Less soluble because of the common ion. Solubility of calcium hydroxide OH parentheses 2 is reduced because of the common ion. Okay? So, a pretty standard equilibrium calculation. Watch out for the parentheses and the squares and cubes and stuff like that. Okay? If you're calculating solubility in a solution of something else, if one of these is a common ion, that goes in the initial of your equilibrium calculation. How would the calcium, or how would the solubility of calcium hydroxide change in a sodium nitrate solution? It would not change at all. There's no common ion. There are no ions that would interfere with the calcium hydroxide solubility equilibrium. Okay? So it's only if we're adding a common ion, essentially adding a product of that equilibrium, would the equilibrium shift left away from it and make the solubility less. Okay? So solubility reduced because of the common ion. Reduced by almost 10 times as much. Turns out. Okay? Let's look at another way that solubility can be influenced. If the dissociation produces a basic anion, so hydroxide is a basic anion, carbonate is, sulfide is, pretty much any anion that's not one of the pH neutral anions, like chloride and bromide and nitrate. Okay? So those are all basic anions. Solubility will be dependent on pH. Turns out if we have an acidic cation too, that would do it, although we don't really study acidic cations in this course too much. So take a look at addition of strong strong acid to this solution. What do we write to represent any strong acid? H3O plus. Okay. Which of these two ions here, which of these will react with an acid? Carbonate. There's a neutralization that will happen. What does the carbonate ion turn into? Bicarbonate, H. CO3 minus, thus plus water. Okay. So addition of strong acid to the above solution essentially removes carbonate from solution. Through reaction with hydronium, we remove carbonate. Which direction will this equilibrium shift in response to removing that product? Yeah, reaction shifts right. And the solubility of the compound does what? Goes up, increases. So, calcium carbonate is a component of limestone. There are lots of statues and buildings and things made of limestone. What is the specific risk here if there is, say, some acid rain or something in that area? Yeah. Normal water doesn't do much to calcium carbonate because it has a KSP, a very low solubility. But adding any acid will 1 mole of acid will essentially remove 1 mole of carbonate ions and force 1 mole of calcium carbonate to become ionic and washes away. So I think there's a picture in your textbook of a statue from an old picture in 1900 where it looks great versus a modern picture after years of acid rain and exposure to acidity that way, and all the features are lost and it kind of looks like it's worn down much more than just 100 years with. So a similar sort of thing happens when a base is added to a solution which contains an acidic cation. But again, like I said, we don't really deal too much with acidic cations, but the iron Fe2+ ion is acidic, for instance. Adding base would remove it from solution. Same sort of way. Okay?